In this video, we're going to be looking at 3 examples of cases where we want to determine where a power series converges. So in this first example, I have a sum from n equals 0 to infinity of x to the n, and I want to find the x values for which this particular power series converges. So one thing that I want to notice is that for this power series that we have here, the power series is centered at 0. Okay, that means a is equal to 0 in our general power series form here. Okay, my constants in this case also happen to all be 1. The coefficients of the powers of x are all 1. So notice that this series here, the sum n equals 0 to infinity of x to the n, is equal to 1 plus x squared plus x cubed, etc. Okay, so we want to just sort of think to ourselves for a minute about what series this might remind us of that we've seen before, like if x was numbers instead of just x here. We notice that I am multiplying by the same thing each time to get to the next term. So 1 times x is x times x is x squared times x is x cubed. So this series actually looks geometric. Okay, in particular it's geometric where a is 1, the first term is 1, and the common ratio that we have is x. Okay, so we can apply the geometric series test to this series. And we're starting with basically the simplest power series we could have, a sum of powers of x with all coefficients of 1, just to get started. So here we can say, so by the geometric series test, our series converges. Okay, well, the geometric series test tells us that a geometric series converges when the absolute value of r is less than 1. So in this case, it's for the absolute value of x less than 1. Okay, and diverges, otherwise, but for the absolute value of x greater than or equal to 1. Okay, geometric series test also tells us that its sum, the sum of this polynomial, the sum of this series, is a over 1 minus r, or 1 over 1 minus x. So this gives us our first function here that's equal to our power series. So we can say, so 1 over 1 minus x equals 1 plus x squared plus x cubed, etc. Okay, and it's only equal to 1 over 1 minus x over the interval where it converges. So this is for the absolute value of x less than 1. Okay, so we've answered the question. For what x does this series converge? This series converges for the absolute value of x less than 1 by the geometric series test. Okay, so we also want to use this example to introduce some terminology that we're going to be using when asking questions about where a power series converges. So what's some of our terminology? Well, we would say that the interval of convergence for this series is the following. So the interval of convergence is some terminology that we'll use. Say the interval of convergence, okay, for this series is that x is between -1 and 1. Okay, so when we say the absolute value of x has to be less than 1, that means x is between -1 and 1. Okay, or in interval notation here, we could say the interval of convergence is -1 comma 1 with just our parentheses there, curved parentheses. Okay, we would also say the radius of convergence for this series is 1. Oops. The radius of convergence for this series is r equals 1. Okay, so why do I have this terminology called radius of convergence? Well, if I draw a picture of the interval that I have, and I know that I'm centered at 0, okay, my interval here of convergence goes from -1 to 1. Okay, so this, everything in here is the set of all x's for where my series converges. The radius is just the distance from the center to an edge. Okay, so that's where I'm getting that radius is 1. Okay, so I have this interval here, includes all values in between, not including -1 or 1. And I have this terminology where I would say that the interval of convergence for this series is the interval from -1 to 1, and the radius of convergence would be equal to 1. Radius, again, just being the distance from the center to an endpoint. Okay, and our interval here is symmetric about that center. So now we're going to see that in future questions, instead of just asking for what x does in power series converge, we're going to ask to find the interval of convergence, which is saying what's the set of x's where the series converges, as well as the radius of convergence. Okay, so we want to now find the interval and radius of convergence for this series. We have a sum from n equals 0 to infinity of x to the n over n factorial. So again, notice that this series here happens to be centered at 0. Okay, we're just starting with some simpler examples. Looking at the form of my series here, I also notice that I have a factorial involved. Okay. Another thing to notice is that whenever I'm going to have this x to the n, x could be any number here. I can think about trying different values for x, different numbers in there. I'm going to have a number to an n. So this x to the n is an exponential type thing. Okay, so when we think about what kind of convergence tests were useful when I had an exponential like 2 to the n or -3 to the n, and factorials, n factorial, 2n factorial, etc., that was the ratio test. So we're actually going to see that on pretty much all of our problems dealing with finding interval of convergence and radius of convergence, we will be using the ratio test. There might be a few examples where the root test would be helpful, okay? But because your power series here is made up of some coefficients of exponential type things, you're going to have a product of something and an exponential. So the ratio test is going to be helpful. Okay, so keep in mind that the test we're going to use almost all the time with finding interval and radius of convergence for power series will be the ratio test. Remember that the geometric series test is really a special case of the ratio test where that r is constant instead of being a ratio of an plus 1 over an, being something in terms of n. Okay, so we're going to apply the ratio test to this series here and see if that helps us, or how that helps us determine the x's for which this series here actually converges. Okay, recall that we said that for our power series, the power series always converges at the center. So we're trying to find if the interval of convergence is just going to be 0 in this case, or if it'll be more than that. So I'm going to start by saying, okay, we know it converges at 0. So if x is not 0, I'm going to apply the ratio test here. So notice that means I'm looking at the limit as n goes to infinity of an plus 1 over an. And you'll see in a minute why I'm excluding 0 here. I'm going to end up with 0 in a denominator. So we just want to make sure we're not dividing by 0. An plus 1 would be x to the n plus 1 over n plus 1 factorial. Divided by an is going to be times 1 over an here. So we'll have n factorial over x to the n. Okay, so notice that I ended up with an x in the denominator. That's why we're excluding the x equals 0 case here, plus the fact that we already know that this series will converge at 0. So we're looking to do some simplification here in our limit. So notice that this is x to the n times x, n factorial. N plus 1 factorial can be written as n plus 1 times n factorial. And then we get some nice cancellation. So the x to the n's cancel, and the n factorials cancel. So the absolute value is really important to keep around here because x could be positive or negative. So we need to rewrite this as our limit as n goes to infinity of the absolute value of x over n plus 1. I can bring the n plus 1 out of the absolute value because n plus 1 will always be positive. Okay, so this is saying what's the limit as n goes to infinity of some non-zero number x here divided by n plus 1 as n plus 1 is getting bigger and bigger and bigger. Well, no matter what this x is here, it's some finite number divided by something really big, that limit's going to be going to 0. Okay, so then we need to draw some conclusion here about our series based on this ratio test. So we can say, since this limit here, okay, equals 0, okay, for all x except 0, but for all x not 0, okay, and we know that that value is less than 1, okay, then we can say that the series converges for all x. Okay, so we showed that for all x not 0, series converges by the ratio test, and we also know that it must converge at 0 because it's the center. So we can overall conclude that the series converges for all values of x by the ratio test. Okay, so just like in our other convergence test examples that we did in previous sections in Chapter 11, I need to say the name of the test that I'm using and what my overall conclusion is about convergence. And then additionally here I need to state what my interval of convergence and radius of convergence are. So the interval of convergence, if it's all values of x, is negative infinity to infinity. Okay, so in terms of a number line picture, I'm centered at 0, and I'm including all values on the number line here. So when my radius of convergence, excuse me, my interval of convergence is negative infinity to infinity, my radius of convergence, we say, is r equals infinity. Okay, distance from 0 to infinity, we're just going to call infinity in terms of this radius of convergence. Okay, so let's look at one more introductory example. Here I'm interested in finding the interval of convergence and radius of convergence for the sum from n equals 1 to infinity of n factorial times 2x minus 1 to the n. Okay, so here notice that I do have not just x to the n, but something here raised to the n. So we want to try to identify what our center is. Quick way to identify the center is going to be where whatever is inside that parenthesis equals 0. Okay, so we see that that would be x is a half. So it turns out that this is going to be centered at a equals 1/2. One other way to see that that's what the center is to have done a little bit of factoring. So I could have rewritten that as n factorial 2 times x minus a half to the n, and then written that as n factorial 2 to the n times x minus a half to the n, and then I have that in that x minus a to the n type form. Okay, but the quick way to do it was to say, okay, what x value would make this inside 0? That's where I'm going to be centered. Okay, so again, I have some kind of factorial thing, an exponential thing. So I'm thinking about using the ratio test. Okay, so we can say, use the ratio test, which means I'm going to be looking at a certain limit. I can also exclude the center case because I already know it's definitely going to converge at 1/2. So for x not equal to a half, I could be looking at the limit as n goes to infinity of my an plus 1. So that's n plus 1 factorial 2x minus 1 to the n plus 1 divided by an. So that's n factorial 2x minus 1 to the n. Okay, so we're going to look to simplify this a little. So we have n plus 1 times n factorial is how we can rewrite the n plus 1 factorial. I can write 2x minus 1 to the n plus 1 as 2x minus 1 to the n and 2x minus 1. Okay, so this is n factorial and 2x minus 1 to the n. So this is just to help me see how that cancellation is all going to occur. So what do we notice here? Well, I've got a limit as n goes to infinity now of n plus 1 times 2x minus 1 in absolute value. Again, because n plus 1 is always positive, but different values of x could make 2x minus 1 negative, so I do need to keep those absolute value bars there. So notice that if x is not a half, okay, this is some non-zero number times something that's really, 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 really big, so that limit is going to be getting quite large, okay, if x is not a half. So we can say that, so by the ratio test, well, if we got this limit that equals infinity, okay, equals infinity, and infinity is clearly bigger than 1, by the ratio test, the series diverges for all x except that center value of x equals a half. Okay. So when we go ahead to say where the series converges, this is the worst case scenario where it only converges at a half. Okay. So except at 1/2, since the series must converge at its center. Okay. So we can say that our interval of convergence, oops, in this case, interval of convergence, is just the point 1/2. Okay, so it's not much of an interval, it's really just that one point. So to denote just a single point, we just use these curly braces. Okay, it doesn't include on anything on either side of that, it's just the point 1/2. And for the radius of convergence, we would say that the radius is 0, because I go 0 away from 1/2 to get to any other values here. Okay. So this gives you an idea of 3 sort of basic examples of finding interval of convergence and radius convergence. The next video will summarize these different cases that we can see occur, and then the final video will look at a more involved, maybe more common type example that will arise in finding interval and radius of convergence.